Good morning, chemistry students. This is Mrs. Krumschreider, and today we are doing our Chapter 7, Day 4 notes. We're going to start at the volume of a mole of gas and continue through the end of Chapter 7, Section 2. Again, we want to think back to the ways that we measure matter, and the three ways we can measure matter. We can count. And again, on your chemistry toolkit, which you probably should have out at this point, you have three conversion factors for counting depending upon what the substance is. If I have a mole of element, I have 6.022 times 10 to the 23rd atoms of that element. If I have a mole of molecular compound, I have 6.022 times 10 to the 23rd molecules of that compound. If I have 1 mole of ionic compound, I have 6.022 times 10 to the 23rd formula units of that ionic compound. So those were your three conversion factors for count. We also talked about the fact that another way you can measure matter is with mass. And again, for mass, you have a tool on your chemistry toolkit called molar mass, which has some number of grams of substance over 1 mole of that substance. Again, remember that number that goes in front of grams comes from your periodic table. You have to be able to correctly write the chemical formula of the element or the compound, and then use the average atomic masses on your periodic table and the number of each atom to calculate and add up the molar mass. So what's left, right? Our third way of measuring matter was by volume. And today we're going to be seeing how we can use the mole to measure volume. So we're going to start with the volume of a mole of gas. And this goes back to Avogadro again. And he had what's called a hypothesis, right, which is just an educated guess. And his hypothesis said, or states, that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So this is kind of what he thought and believed. He said that if I have two different gases, but they are at the same temperature, they are at the same pressure, and they're equal volumes, then I have to have the same number of particles of those two different gases. And again, the reason for this is because gas particles are far apart, so the size of the particles doesn't affect their volume. So basically kind of what we're saying is, if we have our classroom and we fill it with 15 basketballs, and imagine those 15 basketballs are moving around and filling up our classroom completely. Now, if we have 15 golf balls instead occupying our classroom, they still have equal volumes because there's so much space between the particles that it doesn't matter how big or how small the particles are. Okay? So we talk about what's called standard temperature and pressure, STP. And standard temperature and pressure means a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals, which is the same as 1 atmosphere of pressure. Okay, so by definition, standard temperature and pressure is 0 degrees Celsius and a pressure of 101.3 kilopascals or 1 atmosphere of pressure. 101.3 kilopascals is the same as 1 atmosphere of pressure. And this is important because at STP, so at this standard temperature and pressure, 1 mole, or remember, we're talking about 6.022 times 10 to the 23rd representative particles of any gas occupies a volume of 22.4 liters. So what we're saying here is it doesn't matter what gas I have. If I'm at standard temperature and pressure, so if I'm at 0 degrees Celsius and a pressure of 101.3 kilopascals, if I have 1 mole of that gas, if I have 6.022 times 10 to the 23rd particles of that gas, let's say inside a balloon, then the volume of that balloon is going to be 22.4 liters. This is what's known as molar volume. So molar volume is the quantity or amount, 22.4 liters of a gas. And molar volume is used to convert between the number of moles of gas and the volume of a gas at STP, at standard temperature and pressure. So again, this gives us another conversion factor for our chemistry toolkit, right? And this is really our last conversion factor, because right now on your chemistry toolkit you have those 3 conversion factors for count, because that's one of the ways we measure matter. You have molar mass conversion factor for mass, because that's a second way to measure matter. And now you're going to have a 5th conversion factor total on your chemistry toolkit for how we measure matter using volume. So again, this conversion factor has a name. It's called molar volume. And our conversion factor is that 22.4 liters of gas over 1 mole of gas at STP. And again, power of this conversion factor is depending upon where I need my units to be. I can flip this upside down. Okay, so this is that last conversion factor for your chemistry toolkit. Make sure you have it in your notes, and then again, I would encourage you to pause the video for a moment and add it to your chemistry toolkit. So let's take a look at a problem that involves this molar volume. Sulfur dioxide is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.60 moles sulfur dioxide gas at STP, so at standard temperature and pressure. So again, story problems are the standard in chemistry. So again, I like to summarize what's in this little short paragraph so that I don't have to keep looking back at it, okay? So this problem is asking me to take 0.60 moles of sulfur dioxide, so I should write the formula for that, right? That's a molecular compound, 2 nonmetals, so my prefixes become my subscripts, so it's just SO2. And we want to know the volume in liters of SO2. So again, the first question kind of here is, do I have a tool on my toolkit that has moles and liters in it? I do, right? It's molar volume. To use molar volume, I have to be at STP, which I am. So I'm going to be able to use that tool. So again, I start every problem the way I do every problem. I start with my given, which is the 0.60 moles of SO2. Moles have to go on the bottom so that they cross out. Liters of SO2 are going to go on the top because, again, this is my tool, right? This is my molar volume tool that I'm using. Moles have crossed out. I'm left with liters, which is what I want. Again, when I look at this new conversion factor, right, in front of liters is 22.4 and in front of moles is 1. So in front of liters I need 22.4, in front of moles I need 1. On my calculator again, right, I'm multiplying because they're both in the numerator, so I'm going to do 0.6 times 22.4. Now again, I need to pay attention to significant figures, right? This number here has 2 significant figures, this 6 and this 0. This is just a placeholder, so it's not significant. My molar volume has 3 significant figures, and again, this is sort of a definition, so it's unlimited. Okay. And realistically, I even could say this is a definition, and so it's therefore unlimited. Okay. So I should only have 2 significant figures in my answer, so you should get 13 liters of SO2. So that's our first example. We're going to look at another example that's a little bit different type of problem. Because sometimes you're going to be asked to calculate density. So know that different gases have different densities. And one of the ways that you know this, maybe you've not heard it in science class before, but one of the ways you know this is when you let go of a helium balloon, what happens to it? It rises, right? It flies away. Why does it do that? Because helium is less dense, helium gas is less dense than the gases that make up air. So helium gas in air is going to rise, okay? And you lose your balloon if you let go of it, okay? So different gases have different densities. Usually, the density of a gas is measured in grams per liter and at a specific temperature. So if your textbook asks you to calculate the density of a gas, you should assume they want it in grams per liter. So you can use the density of a gas at STP and molar volume at STP to calculate the molar mass of the gas. And so that's what we're going to take a look at in our example. So the density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP. What is the molar mass of the compound? So again, we have a story problem. So this problem is asking me to take 1.964 grams per liter and figure out its molar mass. Now, what are my units of molar mass going to be? If you're not sure, look at your chemistry toolkit. That tool that is labeled molar mass, right, has units of grams per mole. And they do tell us that this is at STP. So notice what I kind of have to do in this problem, right? I need to convert or change. Gram stays the same, right? I just really need to change liters to moles. Do I have a tool on my toolkit that has liters and moles in it? Yup, right? It's molar volume. What has to be true for me to use molar volume? I have to be at STP, and I am. So, again, I'm going to start with my given. Now, it's important that I keep track of whether my unit's in my numerator or denominator, right? And liters is really in the denominator. That means to cross out, liters has to be in the numerator and moles has to be in the denominator. Oops. Okay. So liters are crossing out and I'm left with grams per mole, which is what I want because that's what my units of molar mass are. And using my chemistry toolkit, right, we know that 1 mole has a volume of 22.4 liters at STP. So, again, on my calculator, I'm going to do 1.964 times 22.4. Now, again, I need to pay attention to significant figures, right? This has 4 sig figs. This is a definition, so it has unlimited sig figs. So my answer should have 4 significant figures. So I look at what my calculator gives me, and I'm going to do that really quick. So 1.964 times 22.4, right? My calculator gives me 43.9936. I want to have 4 significant figures, so I'm going to write it as 44.00 grams per mole. That's the molar mass. Oh, actually I can do, let me, right, actually, come on. 43.99 would stay 43.99 because the next number is a 3. So 43.99, 44.00, they're the same, okay? It doesn't matter to me which way you write it realistically, okay? So you're going to have some problems on your homework where you're going to be asked to calculate the density of, or the molar mass of a gas given its density, okay, and it's using molar volume. So the last thing then in this section is a mole roadmap, and we're going to kind of review the conversion factors you have, right? So the first ones we talked about were for counting, right? Because that's one of our ways of measuring matter. And when we count, we're talking about representative particles, and we're going to use Avogadro's number. Right? And so there are 3 of these depending upon your substance. I can have 1 mole of element over 6.022 times 10 to the 23rd atoms. And again, I can flip it. I can have 1 mole of molecular compound over 6.022 times 10 to the 23rd molecules of that compound. And lastly, I can have 6.022 times 10 to the 23rd formula units over 1 mole of ionic compound, right? Those were our ways of measuring matter as a count. Our second way that we talked about measuring matter was mass. And that tool has a special name. It's called molar mass. Right? And our tool for molar mass is 1 mole of substance over our number of grams of that substance. And remember, this number comes from adding our average atomic masses on our periodic table. And again, remember, the power of all of these is I can flip them depending upon how I need them to be. Lastly, our third way of measuring matter was by volume. And again, that tool has a special name. It's called molar volume. That tool is 1 mole of gas over 22.4 liters of that same gas at standard temperature and pressure, right? A temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals, or 1 atmosphere of pressure. Okay, so you should have these 5 tools on your chemistry toolkit. So your homework is homework number 5. On page 186, you're going to do problems 24 through 28. Again, you need to show all your work. This is not a homework assignment to type. Do not try to type this. Okay, hand write this out on a sheet of paper showing me all your work. Remember, the only problem you don't have to show work for is molar mass. Okay, otherwise, again, you're going to show work like this. You're going to show work like this. Okay, you're going to show your work for all of your problems. If you don't, I'm going to return your assignment to you and expect you to redo it, showing me all your work before I give you credit for it and before I mark you present for attendance. So, have a great day, and I will talk to you tomorrow.